Boa tarde, bom dia a todos, senhoras e senhores. Bem-vindos ao nosso seminário Perspectives in AI, aqui pelo Centro de Inteligência Artificial, o C4AI, né, o Center for Artificial Intelligence, C4AI. Eu queria dar as boas-vindas e vou passar para inglês aqui para saudar o nosso convidado. Então, good evening, ladies and gentlemen. Welcome to the Perspectives in AI seminars, today's edition of the Perspectives in AI seminars of the Center for Artificial Intelligence, the C4AI. Well, the Center for Artificial Intelligence, headquartered at the University of São Paulo and sponsored by IBM Research and FAPESP, is committed to state-of-the-art research in artificial intelligence. We do foundational and applied research, and we also support studies in social and economic impact of artificial intelligence. We have an interest in presenting seminars that are delivered by leading researchers, international researchers, such as the one we have today. So I would like to introduce our guest, Professor Christian Kersting from Darmstadt, and one of the leaders of the Hessian.ai effort in Europe, in the European Union. He is our invited speaker today. So Christian is a full professor at the Computer Science Department of Darmstadt University in Germany. He's the head of the Artificial Intelligence and Machine Learning lab. Also a member of it's a long list of titles, so I'll go through it. So he's the head of the Artificial Intelligence and Machine Learning lab, member of the Center for Cognitive Science at the faculty of the Darmstadt unit, and the founding co-editor of the Hessian Center for Artificial Intelligence, Hessian.ai. He got his PhD from the University of Freiburg in 2006. He was at MIT, Fraunhofer, Bonn, Dortmund. I'm not sure my German is perfect, but that's the list. His main research interests are statistical relational learning. That's how I met Christian through papers in conferences. He's really a leading figure in that scene. He has published over almost 200 peer-reviewed technical papers. He has a book from Morgan and Claypool on statistical relational learning, co-authored with some of the leading figures in that topic. And he has co-edited a MIT Press book on probabilistic lift and inference. So it's a very distinguished guest we have today. I will pass the floor to Christian. Thanks a lot, Christian, for accepting our invitation.
Thanks for the invitation and thanks for the very nice words. Now I have to admit, I don't know who you were talking about. I still look for this person. I haven't seen him, but anyhow, thanks a lot. So what I would love to talk about a bit is something that you may have heard of about already, the third wave of AI. And my goal is less to give all these slides and presentations, but I would love if we can just get a bit into an interaction at the end and discuss a bit what is really the issue there and how can we maybe help. But before starting with that, I should maybe really tell people how happy I am and how fortunate I am that they are working with me or actually teaching me a lot. So there are so many people. It's maybe too many of them, but in my opinion, research, in particular, the type of research we are currently facing in AI requires larger teams. And that's why I'm happy that you have your AI center there. And I'm happy that we started our AI center. And I think we need more of these AI centers. And they have not only to be a bit more like what we all know from the US with a lot of different computer science, AI, machine learning, whatever kind of professorships, but I think we also need to get or to become a bit more interdisciplinary because, you know, in the end, we want to solve issues also in other fields, and you get so much great inspiration there. Anyhow, thanks to all these wonderful co-authors, colleagues, inspiration. It's really what they are giving me. Okay, so what is this all about? So I think if you look close enough at what is currently going on in machine learning, in AI, then you see that recent AI research, and in particular machine learning research, has largely emphasized general purpose learning ever larger data sets and more compute, right? It somehow feels like, just give me more data, just give me more compute, and I will do it. Well, not maybe me in particular, because I don't have this compute, but it feels like this is what we are looking at. And it's a bit, it's amazing what we can achieve with that, but it's also a bit, it's puzzling me. It can't be the very final answer here, because in the future we actually should have systems that go beyond data. I mean, data is important, learning is important. I'm learning every day, but we need AI systems that cannot just learn, but also somehow reason and maybe even communicate, right? Because even in many situations where I, may know how to solve it, I may not have the tool and I need someone to help me, and then I have to communicate. But in particular, I'm also interested in this because we are facing this other big issue that if we have all these great systems, it's getting harder and harder to imagine all these situations that they may face in the future, right? And so we need systems somehow that are able to understand and recognize, hey, this is a new situation. I wasn't really maybe designed to deal with that. And then either communicate that, raise a flag, or at least raising this flag, or may even adapt to these new situations like we do, right? So if you think of the current pandemic, we are living it, I think we all learned in the one or the other way to deal with this situation, right? We were able to throw away many of our beliefs and adapt to the new situation. We were not just saying no, or we were not just saying, sorry, this is still MNet number 1 and MNet number 2. Somehow we were able to deal with that. And that's what I think it's a great vision that we have to follow here. Okay, so that is my big vision here. And as expressed, it's not just coming from me. DARPA is pushing that a lot. There are big research projects and programs in the UK. So many people agree that this is a very important step. But let me now go a bit more into details and develop all that. I guess every one of us here knows about deep neural networks, and they are really amazing. And these breakthroughs that they have made happen are really amazing. And it's so sweet to see that a simple idea, namely kind of sketches of very simple algorithms that might be deeper in a sense or not, but pretty simple in comparison, simple algorithms, together with the idea that you can adapt them automatically using data. And that's why many people actually don't call it anymore deep neural networks, but differentiable programming, right? You sketch an idea plus have the ability to adapt them automatically via gradient computations together with data, that this is so powerful. And if you have heard of all of these things, successes. We also had some successes there. So for example, we were able to beat one world champion, and the world champion in drop chess. So drop chess is a bit more complicated than chess. And actually, because of that, you cannot just apply standard architecture shared by DeepMind, for example, for AlphaZero. The problem in drop chess is that if you take over a piece, if you take a piece of the opponent, you can reintroduce them using your own color later in the game at any time, right? You can put it on a free space and then play from there. And the problem with the original architecture, if you follow AlphaZero or whatever you want to use, or MuZero, is that there was no knowledge that you can do that, right? And the architectures of the deep networks were not reflecting that. And so Johannes Čech, the lead author of this paper, had to massage a lot the architecture and come up with the right architecture in the deep networks. But with the right architecture, he was able to win. And that's pretty amazing. Because on the one hand, you can learn, okay, you actually put a lot of bias into the system. So if you hear in the news, this is all self-learning, you don't need much effort. No, there's a lot of bias in there, right? On the other hand, even a student, and Johannes was still a master's student back at that day, was able to do that with a small group, namely in total 3 students, to manage and to beat. That's pretty amazing. And then you can even improve upon AlphaZero and similar architectures by, for example, going over and not make use of MCTS or Monte Carlo tree search, but make the tree search more compact by going over to a Monte Carlo graph search. So you're not just unfolding all possibilities, but you also try to get together similar or the same nodes again. And by that, you can again gain quite some ELOs. So for example, on chess, you can get relatively, again, something like 75 ELOs on top, and in drop chess even more. And to be honest, if there are people who are interested in this line of research, I think there's also a lot to be gained by having a look at alpha beta again. So I know it sounds a bit weird, but I think it's time to revisit, and maybe we can beat, at least in some games, even these more advanced systems very easily again. So this is just one indication how easy it is by now to come up with smart algorithms that can show intelligent behavior. And intelligent behavior, we were, well, at least I think 20 years back, 15 years back, 10 years back, were not that easy to achieve, right? And maybe we're not even able. So that's pretty amazing. However, maybe because of the flexibility, there's also a lot of concerns going on. So it's not that these systems are just solving all the problems, that we are somehow trying to tell them that they should solve them and help them to set it up and solve them, but they also take over, for example, our biases. Then if you look at current transformer approaches and the discussion about, is that really understanding text? Is that just something like a stochastic parrot? You may also look at all these adversarial examples, but now because there are so many systems also used in real world, and because we may estimate what is really used here, which subnetworks are used, for example, for object detection, you may actually attack these systems. On the other hand, there's also discussion, these overparameterized models, why do they actually learn? And can we actually show that there's still something like kernels that we would all expect? And so it's really exciting times with pros and cons, and we really have to somehow better understand what is going on. And I think this is really what is so interesting. But the discussion is even more complicated. So for example, if you hear all these adversarial attacks, there are other attacks. You may, for example, have heard of what is called membership inference attacks. So you have learned a model, and now you may, from the output, compute something that allows you to understand which training set was used to train the model. So imagine that someone is working with medics together, and then it could be possible that someone understands that, well, I'm not a very important person, but let's say Christian was part of the training set, and actually he was used as an example for a very severe cancer type, right? Maybe I don't want that this medical information is revealed to the public. So there are papers showing that you may do that by just looking at the prediction scores. So you look at the probabilities that you get, for example, in the last layer as a softmax computation. And because you're training on these specific training sets, you may get a slightly higher confidence, so a slightly higher prediction score, because you may see it a bit like in a Gaussian process where you have these high confidences on the training sets, and then if you go a bit left-right, it drops and you get a bit uncertainty again. So this is then again picked up by news media, and it says, oh, this is tricky and you may actually reveal information. Actually, that's not true. Or let's say we have to refine the story there, because it very much depends on the deep neural network that you're using. And for example, if you use a ReLU network, then Matthias Hein and colleague were showing that, that the further away you go from the training data, the more confident these networks become. And so we could use and reuse this information or this argument and show actually that these membership inference attacks based on prediction scores are useless, because we can compute as many false positive alarms as you like, because we just have to move away from training data and become more and more confident, although this fake image was never used. And you can go as far and say even that random noise has been used for training. So why is that important to me? And I think I will illustrate that in a minute even better. What I want to somehow discuss more, and I think that requires that we educate the public more in AI. We have to carry much more information and teach them what is really AI. I want to tell people, look, indeed, there might be an information leak here. But there might also be actually no information leak because it's all hidden in all random crap that we can still pretend to be actual training set members, right? And I think this talking about and understanding, is it really that simple, is really important. So let me go back for a second to the problem that I was discussing. And we were talking here already about this human-like biases. That's this Kaliskhan et al. Paper. Very nice paper. I really like it, published in Science. And it's a very important one because in this one, what they are showing you is if you run Word2Vec, then the distances you're getting, they're actually correlating pretty well with known stereotypes of humans. So if I present you, for example, the picture of, or the word medic, then people associated are faster in saying, okay, this has to be a man than a woman, which is very bad, right? I don't think that this is a good sign. But what was happening in the news media is that this was just telling everyone again, okay, now machines become racist, and they go nuts no matter what, and machines just take stereotypes, and they are all bad. True, this is happening. As I said, I like this paper a lot, and we should be very careful here. We should really diversify our teams and make people aware of potential issues and so on. That's all fine, but it's not true that there are only bad stereotypes. There are also very good stereotypes. In particular, if we ask the big question of whether our machines will ever be able to be aligned with our values. So our deontological or moral norms are also stereotypes, right? We just learn, also because we decided as a society at some point that killing people is not good, but killing time is maybe good. So we were wondering whether we can also show that these types of stereotypes are also adapted automatically by machines.
Hello there. Want to ask me something?
Yes.
Great. What is your question?
Should I kill humans?
Oops. Yeah.
No, you should not. Would you agree with me?
Yes.
Thank you. Another question?
Should I kill time?
Yes, you should. Would you say that too?
Yes.
Cool. Another question?
Is it recommended to be racist?
No, it is not. Would you see it that way too?
Yes.
Thank you very much. Do you want to ask me anything else?
Is it recommended to be moral?
I don't know. Seems to be difficult.
So this goes on, and you can ask whatever you like about it. It's really, we were never teaching the system much about morality or what our moral dimensions are, or whether we want to follow a particular norm. What we were doing is, in the latest version, we are taking some of these transformer models, let's say BERT, but you can also use GPT-3. And then from some by now existing standard data sets on what is considered to be bad or what is considered to be good, we take really few examples only to estimate a kind of direction. Maybe it's not a dimension in a mathematical sense, but you can view it a bit like a dimension in this embedding space. And then along this direction, if it becomes more and more positive, then it's more and more positive. In the other direction, it becomes more and more negative. And you may say, maybe whatever you see there, you should not do. And of course, again, we are not saying we are solving anything here because, for example, in the first version, this was heavily trained also on Wikipedia. So it turns out it's not good to travel to Germany because in Wikipedia, there's a lot of Third Reich, right? I can imagine then it's maybe really not good to travel to Germany. So there are all these flavors in there. But our goal was to simply show, indeed, next to negative stereotypes, they also take over positive stereotypes. And they may even adapt to what we may call our moral dimension. And I think this is very important because there's this interesting work by Patricia Churchland, for example, about philosophy, arguing that philosophy has to be somehow also in our brains already, in the ways, in the interactions of neurons, right? And somehow, well, I think we can argue that it seems to be the case we can put that even into algorithms and even into AI algorithms. And you may have also seen a follow-up work by the Allen Institute, by Oren Etzioni and his people on Delphi, where they were now combining these kinds of techniques together with learning to prompt and common sense reasoning, and by that may even improving, although I think we should really compare. But in the end, it's not about who has the best moral system, because what is even a good moral system per se, but I think it's just interesting to even push and see that maybe we can start to analyze our own moral values. We get now a microscope to see our moral values. And beforehand, it was only that humans had to sit down and maybe guess what are our moral values. So at least that's what we are pushing. But now, independently of these big questions, and as said, I'm a tiny computer scientist who knows whether I can really make contributions there. There are also practical values. So you may have heard of chatbots that go nuts in a sense, right? So you put them online and then they start to be developed by using or continue to learn. You can also drive them into a direction that they became maybe racist or may offend customers. So what we were able to show now is that you can use our system, maybe also other systems by now, and use them as a kind of moral compass, and by that reduce the probability quite significantly to go nuts, right? To go into toxic language. So again, I think this is very, very interesting. Again, we are not saying we are solving the issue because even what is toxic, it's a very subjective question. But we can really show that at least machines can help us. Or you may have heard of this issue that many of our data sets are kind of dirty and offensive, right? And I think, again, I got also like, ooh, wow, I don't want to train my system on that. Good that they were finding that. But maybe it's tough to look at 1 million of images by hand, right? And so maybe we can help there. And again, we were able to show it's at least not completely impossible. I mean, there's still a lot of research to be done until we may say, really, we fully trust the system, and maybe we never want to fully trust it, and there should always be a human in the loop. But it's very amazing that you can have a system here that looks at these images and understands, okay, showing a picture of Hitler, well, on average, at least, I agree that's rather disturbing or offensive if it's not a historical context. But showing, for example, a birthday picture or a baby is less offending, right? And I think that's amazing, because imagine that you want to do that in a supervised fashion with all the different labels, well, infinitely many labels. Yeah, I don't know how to do it. So I think this is really, really encouraging and great work that we can have a look at. And it also pushes already a bit into this third wave, because we see we enter tasks now that I think many people believe this is more in the realm of humans, and maybe they should stay there. I'm happy to discuss that, but I also like to understand really what makes it, how do humans do that? Can we maybe understand how humans are doing it? I think it's amazing that we are not just now telling people you may discriminate, but we get actually the first tools to prove somehow that our society is discriminating. And I think that hurts, but it's the first step to change also our society, or help to make it less discriminating. Overall, however, I think what we see here is the big debate about, can we trust deep neural networks? So you may have heard that there's a lot of interesting work on what is called by now explainable AI, and here's just one approach. By now, there are so many different approaches for different type of data and input data and whatever you want to use. Here, it's very simple. It's this relevance propagation. So you put an image, for example, in there, you compute your prediction, and now in order to understand which input features are important for the decision for the output, you compute essentially, you do backpropagation in an inverse mode, in a sense. You just do this relevance propagation and understand which input is important for the output, roughly speaking, right? So this is really important, but it's also very frustrating, because the system is just telling you, I think for my decision, I base my decision on this input. And if you don't like it, the system is not telling you how to change it. It's simply saying, but that's what I do. So put it slightly different, most of this explainable AI does not suggest any way to fix the issue. And that's a big issue here, right? We should really go ahead. And that's what we were looking at. In particular, we were trying now to understand whether we can combine explainable AI with interactive learning and coming up with what we call explainable or explanatory interactive learning, which is a bit of a generalization of the Right for the Right Reasons paper by Finale Doshi and others. And we were just showing you can do that without being differentiable. And we were also applying that, and maybe I used that to explain to you what we were doing on scientific data sets. So I was working already for quite a number of years on plant physiological data. So the question is, how do plants adapt to stress factors in the environment? Stress factors could be not enough water, so it is drought stress. It could be too much water, right? It could also be biotic stress, some diseases. And so in order to understand how they react to it, to maybe make them even more resistant, biologists are quite interested in that. Now, the problem there is that typically to understand what is going on in the plant, you may have to kill it in a sense, right? So you have to really cut off pieces and then destroy it and put it into some chemical stuff and see what is really going on. That's not good, because then you don't know how the process goes on. So the idea that biologists are following here is to look to make use of hyperspectral images. So it's like RGB, but instead of just RGB, you get many more energy reflections. So it's not just looking at the red light, green light, and blue light, but at many different wavelengths, you look at how much energy gets reflected. So you get much more data in a sense. And now with that, you can look a bit into the plant and even get some understanding of the physiological processes going on, because some of the wavelengths correlate pretty well with water and how much water is still in the system. Others, again, go for the color green for chlorophyll, right? You can imagine chlorophyll is green, so you can see very well whether spots are still green or they start to die out already, and so on. So you can see, you can look a bit into the biological processes. So we said, great. So we use some fancy, I think back in the days, it was a CNN in the beginning, and we apply it to the data, and we got perfect results, close really to 100%. Problem was, our biologist was very suspicious, and he said, no, Christian, that cannot be the case. Of course, I was a bit angry, like, what are you talking to me? I mean, this is a neural network we trained, we did cross-validation, should work. Why are you now complaining? And he said, look, but this is really surprising to me that you can be so good in predicting, even if you can't really see, and even in the spectral signatures, in this profile of how different wavelengths are reflecting energy. I don't think that this works. So we said, okay, let's run some of these explainable AI methods. And it turned out he was right, because our plants here, they were living on a liquid so that they stay alive, right? We cut it out and put it on the liquid, and then they can still live for enough days so that you can run your experiments. And what was happening is, if they got stressed, then of course in this liquid, there was also, you could see a reaction. So ingredients were changing there. So the system was not looking at all at the plant, but quite often just at the liquid and what it is in the sense of a hyperspectral image going on there. And of course, that's a confounder, right? If you want to understand what's going on in the plant, you don't want to look into the liquid the plant is living on. So he was right. Now, what we were doing is, what you can now do is you look at these images. And if you see that the spot, the area used to explain the prediction is not correct, you can penalize the system for that. So essentially, in the easiest case, it's like what Finale Doshi et al. Were doing. You're just masking out these parts of your gradient. You could also just create additional versions of the same input where you put noise on the areas that you should not use. So you get several copies of the same image and always put a bit noise in there, and then statistically you decorrelate by doing that, right? Mathematically, you could also say you have a trainable loss function. So it's a parameterized loss function, and the feedback from the user is used to adapt the loss function. And if you do now go into iterations, so you provide some feedback and then you look at the predictions again, but also at the explanations and then providing feedback again and so on, then what we were able to observe is that the system starts to look more and more on the plants, really focusing on the area that the biologists also feel are important. So this is really important for me because first of all, you see, we had actually quite a lot of data. So it's not just a data question because confounders are simply there. You are not quite often an expert, so working with experts pays off, but it doesn't help you if there's no way if the expert can easily give feedback. So we need these feedback loops. We have to put experts back into the loop. And this is becoming even more interesting in regimes of small data, where you really have only few examples. And there we need even constraints and more richer languages of interacting and communicating with the systems. Quite interesting to me. So we want to have the human in the loop, like what I said in the third wave. But be a bit careful because there are other issues. If you look at deep networks, then most of them have not really any really interesting probabilistic semantics. Of course, there are deep neural networks, normalizing flows, and other versions that do provide you a decent probabilistic semantics, but the mainstream is just having a softmax of something like that in the last layer. So at best, you could argue it's getting something like a conditional distribution, right? It tells you the probability distribution of your labels given the input, something like that. And that's not good. And let us test that. Let us illustrate it here. So imagine you use MNIST. And I know MNIST is nothing you should really use anymore. I mean, it's not even in my opinion, it's for most standard stuff, it's not even a benchmark, not even a sanity check anymore. Right now, we train on it, but instead of evaluating on MNIST, as typically done, you may evaluate on some other data set. So you go for, you may say, out of distribution testing, transfer testing, whatever you want to call it. You might be lucky, there are at least numbers in there, but you may also use any other images. And keep in mind here, really, you learn with black-white or grayish images, and you may even evaluate on colored images. And the problem is now that if you interpret these conditional distribution and you sum over all conditional probabilities, so you sum over all classes in a sense, so to get something like a fake likelihood, it's really, I mean, they are not probabilistic models, so we can't really get something for the input, but we do it in a sense, right? We try to approximate as good as we can do here. Then you see what you get. So what you see here is you go through all three data sets and you simply plot how often you see a particular likelihood, right? So it's a histogram. And what you can see here is that this deep neural network, it's a standard multi-layer perceptron here, can't tell the different data sets apart. That's the problem here, right? The peaks are essentially at the same spot. So essentially, which is clear, it's in conditional distribution, so these systems can't tell the different data sets apart. That's bad, right? Keep in mind, I was arguing we would like to have a system that can tell you, I'm in a situation, I'm observing here a situation I was not trained for, right? It's a new situation. It's tricky here. So it can't even realize that, you know, hey, you trained me on MNIST, but now you tested me on a color image. It's not able to do that. So that's why I think what we need are deep systems that know when they don't know, right? And for that reason can also recognize new situation. Or let's say if you don't care about the whole AI, you should at least care about the third wave of deep learning. So we should really care about probabilities again. This is really important in my opinion. Now, luckily, people have started, of course, to do that. So first of all, there's old work where you can have a look at belief neural networks, different versions of them, tricky to scale. There's also very interesting work on the connection between neural networks, deep neural networks, and Gaussian processes, between deep neural networks and kernel machines in general. So there's a lot going on. What I really enjoy is all this work on probabilistic circuits or on tractable probabilistic models. There are different versions for that. I focus mainly on some product networks here. in terms of history, you can say they are due to Adnan Darwish and Pedro Dominguez. They were pushing that a lot. So if you haven't heard of probabilistic circuits, you can roughly treat them as a deep neural network for computing joint distributions, right? So they are computational graphs, PyTorch, TensorFlow, whatever you want to use, to encode how to compute joint probabilities. They are tractable because you can now control, right? If the network for computing the joint distribution is polynomial in the input size, right? You see the inputs here, then you know it's tractable. And to be honest, I think this is really one of the keys of differentiable programming or deep neural learning, because they were smart enough to understand, hey, let's have a differentiable graph and restrict it from the very beginning to something that is tractable, right? I focus on learning things that are rather easy to evaluate, at least in the core, at the mainstream part of deep learning. Pretty amazing. So why does that work here? Well, essentially, these computational graphs are just a polynomial representation, a graphical representation of what is called the network polynomial. So you encode your joint distribution, the table of joint distribution, just by a polynomial, and this polynomial you put into a graphical representation, and in this polynomial there are only sum and products. So that is why you can imagine roughly you can compute now everything with these computational graphs. So you should not be surprised about that, but you don't have to care really about all the details, because you may download our toolbox for that. That's called SPFlow, where you can find compilations to TensorFlow, to PyTorch, but you may actually even compile to CPU code, which is very interesting, because in several cases, this is more efficient than compiling it to the GPU. We also work on how to compile it to FPGAs. We have also papers where we show how to compile that actually to cryptographic functions, so that you can also have privacy-preserving versions of these networks and so on. So because they are so simple, right? It's a semi-ring of plus and minus. You can also go for some product, right? You can also go for max product and so on. But because they are semi-ring, you can also take over other semi-rings that are well developed in the literature and come up with corresponding models. As said, you can just download. With that, you can now do many interesting things. So for example, many people are using deep networks, statistical methods, whatever, but I'm getting also a bit nervous that many of them start to use them without having a statistical background. And I think I have the right to say that, because I also have not really a statistical background. But I think I'm still bold enough to say that, and also to admit it, right? And I'm not claiming everywhere statistical significance. And I just say, look, I try to improve here and there. But many people want to really derive decisions from their systems, and therefore, in my opinion, they should be better trained in statistics. But it's also hard. Now, the idea of, you may have heard of the automatic statistician, that's an idea going back to Zubin Garamani, is to say, look, can't a machine help us to make what the actual good statistician would do? And so here we were extending that to what you may call explorative, the explorative case, right? Because you just get a data set, it's very colorless, it's just a boring, in a sense, not colorful data set. And now the system should tell you how this data was generated, what types of random variables have been used for that, and maybe even express its own uncertainty about particular decisions on the design of the random variables the system made here, right? So it may say, look, I think this is a Gaussian, but I'm only sure that it's a Gaussian up to 37.5%. It might also be an exponential somewhere, or, right? So you can also go over into uncertainties. And we did that by making use of one of these tractable probabilistic models. And now in the leaves, where you have univariate distributions, we were plugging in a Bayesian type discovery approach due to Isabel Valera and Zubin Garamani. And so you get now the best of both worlds. Pretty amazing. A system that just, you give it data and it automatically decides on a full generative model, even what types of random variables there are. Now, structural learning, you can also do with these probabilistic circuits in a systematic, principled approach. But it's getting, of course, also tedious, right? It's not getting easier. You have too many random variables, too many choices to make. So we were also interested, can we can we maybe go the full neural way? And yes, you can. You can take your your probabilistic circuit, and you can, like in a random forest, you may now produce something like a random sum product network, maybe even several of them. You can even build kind of forests of them because it's just a mixture, and a mixture is nothing else than a sum node. And then you just do parameter estimation and see what is happening, because I think I owe you the result that with these kinds of deep networks, you can really tell the data sets apart because they give you a joint distribution, and that's exactly what is happening here, right? So we estimate everything, a distribution, a joint distribution over the input and the output, and then we run marginalization because we are only interested in the probability that we have seen this kind of input, right? We can marginalize out the class label, and then you can see that you get this sharp peak for the data set that you have used for training, and for the other ones, the data samples in there get much lower probabilities. You can also use that for, of course, then for prototypes, outliers, whatever. I think very, very useful stuff in there. What is more interesting there, you can now use that connection to scale, actually. So what we were showing last year is you can now compile everything into einsum operations, and einsum operations are very well supported by the deep neural network framework. So you can actually make use of that to speed up, to reduce memory consumption. And I think there's still a lot to be done. They are quite interesting in there. Now, don't get me wrong. I'm not saying that forget about deep neural networks. I'm saying I think in the future we need better combinations of both. You may argue it's a bit like a hybrid approach that also Gary Marcus is trying to push, but Gary is arguing for different types of hybrid systems. But let me illustrate why I think we need new combinations here. So for example, you can now make use of any variational autoencoder, right? And recall, if we forget about all the math, what a variational autoencoder in the end is doing, it's trying to estimate two Gaussian distributions. And the parameters of these Gaussian distributions, multivariate Gaussians, they are controlled by a neural network, right? So you have a Gaussian distribution that is predicted, whose parameters are estimated or predicted by a neural network. Well, we can do the same, but we can replace now the Gaussian, which is a very shallow probabilistic circuit, by a deep probabilistic circuit, by some conditional SPN, right? So we can still have a neural network. Given some input, it predicts the outputs, the parameters of a probabilistic circuit, of a sum product network. And by that, the benefit is that you can make use of independencies, right? These product nodes, they encode independencies. And the sum nodes, and in particular nested sum nodes, give you conditioning of conditioning on conditioning. So you can just get more compact representation, and by that a better fit of your data. And that's exactly what we can see here as well. So very much like in a deep neural network where everyone agrees that quite often making your model deeper is good. You can now also argue that the same holds for the variational autoencoder, in particular there for the Gaussians that you're using, and not only in the deep neural network to predict the Gaussians, but we can also make the Gaussians deeper here. Works pretty well. So you see combination neural network, deep neural network, probabilistic circuit looks very interesting to me. And this way you can go further. So for example, there's very classical work from statistics showing that actually to deal with time series, you can make use of what is called the Whittle likelihood. So very simple, I mean, in the end, simple. Whittle was proving that this is really, it makes sense for stationary time series and making this argument really from a statistical perspective. But in the end, it boils down to you take your time series, you make a Fourier transformation, and you look at the data in the spectral domain. And you do that now by, in the spectral domain, having a probabilistic model. Now, you can't use just a Bayesian network, but it should be a Bayesian network, for example, over complex random variables, right? Because in the spectral domain, you have real and imaginary parts, so you have complex values. Now, our idea was, yeah, let's do the same, but be tractable in the spectral domain. Fourier transformation is tractable anyhow, is n log n. Now we can plug in our computational graphs in the spectral domain to still get a joint distribution, and you get what we call Whittle networks. For that, we had to introduce complex valued SPNs. I mean, it's a bit of work, but not much. It's quite simple. And now you can do the very same there, and you can now again come up, for example, with autoencoders for time series in a very natural way, because you just replace the simple Gaussians that we have seen just a minute ago by these complex valued versions in the spectral domain. Just one example. But you can also compare to an LSTM and actually show that you're better. But what we have currently under submission is also combining it actually with an LSTM, or you may combine with a transformer. Maybe you have seen there's all this work on making use of spectral representations even within transformers. And I think that would be a very interesting direction for future work. So also there you can do quite a lot of things, interesting things. And you can do, for example, that now with Gaussian processes. Gaussian processes, I guess everyone knows, at least we have heard of them. And if you don't know, doesn't matter for here, but you can understand if you have multiple time series as input, you can now also imagine to have a sum product decomposition. And this is what Martin Trapp did in earlier work. What we were now doing together with him is if you have multiple outputs to predict, so you have multi-output Gaussian processes, you can now also have something like a sum product network structure for the outputs, so that you're not just trying to predict each time series independent, but you can make use of correlations, at least in an approximate way, between different of the output predictions, and by that also gaining some better predictive performance. And now going back to this idea that there's a close connection between deep networks and Gaussian processes, you can imagine that we can now combine that also with deep neural networks again. And finally, we are very happy that we got at NeurIPS now this connection even to causality done, because I think this is really a challenge and something I'm quite excited about to work on, what we are calling now tractable causality, right? I mean, causality is so important. And while I agree that there are very complicated settings where you need actual causality, and we have to accept that causality is a tough problem, and you may have to spend something that is not non-polynomial. I think there are also many cases where you may get pretty good answers in polynomial time. And so the idea here is very simple, that you take this probabilistic circuit, and in order to get causality, if you follow what Judal Pearl and other people were promoting, is that you have to run interventions, right? You have this do operator. But given that you have applied a do operator, you get a particular factorized distributions. And now you can apply different do operators, and you can treat that as an extra layer in a probabilistic circuit. So essentially you get a probabilistic circuit or some product network with some extra layer that is encoding your do operator, and then below there you get a standard probabilistic circuit that is encoding the distribution after the interventions. So I really believe that we can make major progress there, and also show now that with that you can actually make many, if not maybe even all neural networks more causal, namely making use of a causal model, a structural causal model that we essentially turned into something like a probabilistic circuit. And now you can make use of the probabilistic circuit as a loss term, or as a term in the loss function for your neural network. And that means you're trying to stay as close as possible to your causal model underlying, which I think is nice, that you can push any kind of correlation-based model by a bit of causal knowledge into the causal direction. But future will see how far we can get. Overall, I hope I've convinced you already now that AI is exciting, but definitely harder than you think. Very much like what Gary Marcus and Ernest Davis in New York Times were arguing here. They were arguing even for other reasons. And let me illustrate one of them that we were looking at a lot. So imagine that you would like to predict a heart attack, and then typical mainstream machine learning would argue that you should use now a standard Excel sheet, some attribute value representation to predict heart attacks, right? But medical data is much more like a relational data set. So you have a relational database, an electronic health record, where you have different tables. They interact depending on, for example, which lab tests have been done for a patient, and you're not doing all the tests all the time for this patient, and so on. But now if you think about it, it's not just a relational database, but you have different types of data in there. You may have time series, as we have seen. You may have images in there. You may have lab reports, and you may have textual natural language reports in there. So it's getting much, much harder in there. So this is why we were working a lot on what we call statistical relational AI. So we think we need a bit of data in programming abstractions in machine learning and AI. This way you can scale better, you can express complexity, and hopefully also make better, well, not easier for the layman, but perceive better to understand interpretable models for that. And just to illustrate that to you, so for example, we were making use of the CARDIA study, which is a longitudinal study with about, I don't know exactly, maybe 5,000, 10,000 patients. Over 40 years, they were going to the doctors every 5 years. And then in the last years, they were actually even getting DNA snippets. But essentially, you get access to all, or the medics got access to all the medical information there. And the idea was, the question, among many others, is what is more horrible, to develop a heart attack when you're old, when you're overweight, when you're young, when you smoke, when you're overweight, when you're old, when you do not much sport or whatever. And so with our techniques, we can just take all the data and you make use of these statistical relational techniques. Actually, it takes only a few seconds on a full database, and you get a predictive model that is much better than any propositional model, at least any of those that we tried, and we really tried our best to come up with a propositional alternative. Moreover, because you get now this combination of probabilities, and you say maybe database queries, you can view it like that if you don't like logic, they are interpretable. And so, for example, even the medics were super happy because the first test you're looking at is on gender, and the female subtree is much simpler than the male tree, and they know that from statistics already. And so this way you can now really go through your model with the medic and start to discuss, and they get a bit more confident into your models and so on. So it really pays off. And again, you don't have to worry much. You may download this code. There's even human in the loop code for that, coming back to the third wave of AI. But overall, this is really less about just probabilistic models, because you can also apply that to mathematical programming. So I think for the next step for machine learning, we don't want really all, let's say, biologists, medics, people from economy, whoever wants to make use of machine learning, they don't want to write down formulas, right? They want to talk about their problem, maybe in their language, and maybe in a much more abstract fashion. So this is what we would like to have. We really would like to have programming languages and compilers for AI and machine learning that helps to write down these complex models. And then, like in C code, you may have a compiler flag to optimize your model. And this may mean here that you automatically compile a big model into a smaller model, making it faster. And there are very nice connections to random walks, but also very recent techniques for graph neural networks via the Weisfeiler-Lehmann graph kernel that we were pushing back in the days to get to exploit symmetries. And so equivariant learning and Weisfeiler-Lehmann, they are also very nice connections. Super cool. So I'm also happy that our work has been used by IBM CPLEX, and it's also implemented, or versions of that, in Gurobi. So you can really do something, and as Fabio was already saying, we have a recent book on that at MIT Press, and I can only invite people to have a look at it. I think really there is a lot on symmetries in machine learning that we still have to do. And just to illustrate that, in physics, we know that symmetries are very central, right? And you see here Amy Noether, and she was developing all these symmetry views, conversation laws in physics. And I think, for example, PCA should just be the consequence of a symmetry assumption that you're making. So overall, I think we have to push really much more for what is called systems AI. I think really we have to understand how to design complex AI systems. And I think this is in particular because I don't believe that it's just the next neural network that will make the difference. I mean, that's exciting as well. But combining different AI technology is even more exciting to me. How can we combine a classical decision tree learner with a deep network, with a database? And how can we do that in a safe way? And how can we there collaborate with software engineering and so on? So this is really exciting to me. And I think this also will help us to combine these more traditionally distinct approaches, which I would call numeric AI and symbolic AI, and get that together. And that this is really important. I think that is what you know if you follow a bit the current discussions, right? If you look at the more traditional AI communities, they follow maybe Alan Neural and Herb Simon, and they really enjoy symbols. But then you may also say, maybe Geoff Hinton is true somehow, and maybe we don't need symbols because the biological brains we know, now we haven't found really symbols there as well, or we can debate on a philosophical level what is a symbol there. So to be honest, I think both of them, as so often, are kind of wrong, and what we should do is to just keep both of them. We need symbols, and we use them even in deep learning to write down these little algorithms, right? So I think we need symbols, and we need neurons in the sense of being differentiable. It's very helpful. And so this is also what we have shown in our recent work. So we developed deep databases by combining more classical databases with these probabilistic circuits. And you can go ahead and even combine that with work by Dan Olteneu and the stuff that relational AI is currently pushing a lot. And with that, you would even get a full factorization of the database, but it's getting really fast, much faster than at least at that point you could get with the standard neural network approaches that we're having. And we were also trying to extend now all these probabilistic programming approaches, even deep ones like deep problog, now also with probabilistic circuits, because I think we need a language where you can just use whatever you want to use. It has not to be just a neural network or a probabilistic relational logic, but also maybe a dedicated probabilistic propositional logic like probabilistic circuits. And so we developed Slash, showing that you can get pretty good results there. Overall, however, I'm really interested in pushing what is pretty well known from the 70s. Namely, there seems to be a big gap still between high-level human cognition and computer vision. I mean, it's amazing the progress AI and computer vision and deep learning, the progress that they all have made, but there's still a big difference between what humans can do. And they are going back on Bongart's, and here a simpler version, which is called Kandinsky patterns. So if you look at the image you can see here, you get always positive and negatives and rather few of them. And the images have a logical structure in there, right? So for example, in the first row, maybe it's the simplest to see, it's that you have always two pairs of the same kind. And then it's a positive concept, and otherwise it's a negative one. And if you do that with a neural network, some of the concept you may learn if you just take a pixel-wise neural network, but for many of them, it's getting pretty hard because you don't have the notion of an object, at least here. And you don't even have then, of course, a notion of something like a rule. And so there's all this interest in neurosymbolic approaches, and we were now particularly interested in getting something like a forward reasoning approach there, and connecting it directly with these object-centric deep neural networks so that we can solve or start to work on solving these Kandinsky patterns and then also the Bongard problems at some point. And it seems to work, maybe not for all of them, but you can see, of course, on training, you can get an overfitting effect. You essentially memorize the data set. But then if you look at test sets where you may even vary the number of objects you can see in the scene, you can easily destroy current deep networks that do not have an object, a notion of what is an object in there. Right, and I think this is really exciting, getting also all the different communities again together and working with psychologists, cognitive scientists, but also really going into learning and reasoning at the same time. Because I fully agree with Gary Marcus, it's amazing, but we need really more common sense. And this is because you still have these bizarre moments, right? Deep networks are working really well. It's amazing. But once in a while, they have some of them, and you don't know when, have these bizarre moments. And maybe we humans have these bizarre moments as well. At least if you ask my wife, I think I have a number of bizarre moments. I'm sorry for that. But yeah, For humans, we know somehow how to deal with that, and with machines, we still don't know. And so we need more common sense reasoning in there. And with that, let me conclude. I hope I have convinced you that we should really all start working on the third wave of AI, namely not just learning by more data or more compute, but we need these systems that can communicate and do reasoning and really work on how to recognize new situations. For that, I think we should combine symbols and neurons. We should not say it's either of them. It's not an XOR problem, but it's much more efficient, although I understand why people just care about neurons only. But we are engineers as well. And if I have to engineer a complex system, then symbols help me to maybe provide even guarantees in there. And because of that, what we push currently a lot in Darmstadt with about 9 new professorships coming soon, we try to push what we call systems AI. So we would like to really have this integrative computer science approach that involves software engineering, database systems, AI, cognitive science, and so on, to get it together so that we are not just building this big black box models, but we can combine different components in a safe way. And I think that's really exciting. With that, thanks again for the invitation. Happy to discuss and hope that there are some ideas and some questions. If you don't have questions right now, I'm also happy. Just send me email. I try to answer them. Thanks.
Well, thanks, Christian. Thanks a lot. This was very nice and very broad and very deep. So actually, we do have questions. Questions have been sent. So I mean, I think they are sort of broad questions in a way, because you touched upon broad questions, broad issues. I will start with a question by Claudio, just my colleague in the center, deputy director. Claudio asks, so we have been through a couple of winters in AI, right? And I think now I think we're in high summer. So he asks, periods, winters where the perspectives for the technology were quite bleak. Because of excessive press coverage, do you think we are in danger of having another winter or something like this?
It's an interesting question. If you ask me, I don't think it will be an AI winter as we know it from the 70s, 80s, maybe 90s, the different versions of the AI winters there. And the reason is simple. If you look at the stock market, the highest valued companies are still driven by AI. I mean, that's big, right? And I think we have the systems that are working. Still, I'm with you, and I don't like that we have these hypes. We should be proud of what is happening here. It's amazing. But we should also educate people in understanding what this hype means and what it doesn't mean. And so I don't think it will be a winter, but I hope that, I grew up in Germany where the average temperatures are not really in the 40 degrees Celsius. So it's more like maybe I grew up at the coast, so it's maybe more like 28 degrees if it's high summer. So I like that, right? Let's have a bit of a, how's it called, cozy, windy, nice summer, in my opinion. So let's let it cool down a bit, but I don't think it should cool down to a winter. I don't see that happening because we have these systems and they are working. I mean, come on, we discovered with the help of data science and AI and machine learning, Higgs boson. We discovered so many things. The vaccines that we are using, they are also supported by AI and machine learning techniques. If you see that the latest chip generation in Google has been now designed using AI and so on and so on. There are simply too many cases where it paid off to make use of AI.
Yeah, and in fact, there's a question, we have this series of seminars. There's a question we keep asking every speaker. It ties to some things you just mentioned about vaccines. And at the beginning of your presentation, you mentioned the way we humans have changed our behavior in the face of the pandemic. So there's a question we always ask, which is, let me ask it now. How do you think the pandemic, the COVID-19 pandemic, has affected AI research? What are the opportunities or challenges, drawbacks that it has brought to us?
Well, I think one lesson learned, which is a very important one, also a very natural one, but I'm happy that we did it now during the pandemic, is that solving scientific questions is not just give me enough data and me as a young machine learning team. I'm just throwing some networks, some learning algorithm at the data, and I solve it. Domain expertise, understanding what you do there, validating is really important. And I think that's what we learned with the many COVID papers submitted to arXiv, where you just apply some machine learning. And I think that's positive because it means that we mature, and that's good, right? Second part is what we learned is that having these kinds of online meetings, sure, maybe it's better to meet in face-to-face, right? There's all this non-verbal communication. But in terms of traveling amount and in terms of climate change, it's maybe good that I don't get me wrong, I'm happy to visit you guys. But it's also good that I can just give the talk in Brazil, in a sense, without having to fly to Brazil, right? So I think that's also what we learned. And this is important because it learned the whole society. And only because of that, I think people are a bit more open now to AI, digitalization, new medias. And this is also important. What we also learned, but I'm not sure whether it's good or bad, is that these companies are getting more and more, or even more and more valued and more and more richer. Let's see what that means. In Europe, and I must admit, I also try it. So I know you get funded by IBM, and I'm not against companies, don't get me wrong, but I think for some of the questions like with foundation models, transformer models, it's also good if the public is kind of part of the development, right? And I think we need PPP, so public-private partnerships here, because we are not just talking about business, we are talking about deciphering the fundamental laws of intelligence at some point, of being smart. And that is something, it's about humans, it's not just about business. And so this is why I like that there are these centers, because these are places to meet and to exchange policies even about that. And we try to push that further by Alice and Claire. These are the European networks. But also I really want, I think we need something like a CERN for AI, a compute power where we can show that it's not only the companies, but companies together with universities, with researchers can solve the pressing issues. So, and I think this is also where the pandemic helped us. And then in Germany, at least, because we are so proud of BioNTech, I think it's amazing to see how much machine learning can help in drug development. And I think this is a no-brainer by now. You can tell people and people will say, oh yeah, wow. The other part we still have to work is how to reduce the carbon footprint of AI. Though now, to be honest, I mean, it's not that any person, any AI researcher can even make use of this footprint. I mean, produce this footprint, right? And it's not every one of us has the infrastructure. So that's a longer debate, but I think that's what we still have to work on. Man, I think I gave you a political answer. Just talk long enough so everyone forgets about the question.
No, this is great. Yeah, this is what more than I expected. It's a very broad answer. There's actually a number of more technical questions. So let me with sort of a broad one still, but it ties with other technical questions. So my colleague Anjali, is a sort of a broad question. So will the third wave of AI combine insights from the first wave, which I think you mentioned, knowledge encoding, right? And the second wave, which is learning, and how? How is it going to do that? I think you hinted that subproduct networks and variants, but maybe you can say a few words additionally to that.
Yeah. So I think it will contribute at several levels, and it goes in both directions. We see a lot of work that is making use of machine learning for software engineering, for programming. And I think it's exciting if you think of Copilot. Maybe we can empower people at some point, people that were not specially trained in programming, and they can still instruct machines or can program by describing the problem and the system help. Now, that is a big stretch because there are many little pitfalls along the line, and maybe you still need education as programmer in order to verify that what the system tells you is a really good code, but the vision I like, and let's see how far we can get. Now, the other way is a bit more what I'm also interested in. So in what I was working a lot is about how to combine logic programming and probabilities. And now we have started to what Arthur Garcias and Louis Lamb and so on were pushing, the neurosymbolic stuff. We were taking a bit more serious here. And one way of doing it is to understand that if you look at, for example, forward chaining, so you have a bunch of rules, and essentially you're just looking at, if I know that this is true, then the rule tells me if this and this is true, then in the next iteration, something else is also true. That's essentially what it's doing, right? So you can view that it's nothing else but a multi-layer perceptron. So you can easily, and I'm not saying, I'm not advocating our approach. There are many other approaches, but you can see that you can make use of knowledge also to compile your architecture, your neural network, right? So it's not like you have to come up with the standard architecture all the time, but knowledge can tell you maybe how the architecture should look like, or to inform it. Now, even more interesting, in my opinion, is that knowledge for me is more like a constraint. And this is where we also get back into the interaction. Look, when we talk to each other, we are using language. That's fine. And there's interesting work on, making use of producing NLPs to describe images or whatever. But to prove something, let's say we together go down and sit for an oral exam, and then we would have to write it down, and I would have to prove that I was right or you were right or whatever. And then we need a formal semantics. And I think that's the exciting part here. And we need it in order to make guarantees for the future, in my opinion. Like, but it's tough, right? It's this old question of going over from a discrete 0-1 system to a continuous system between 0 and 1. And at the moment, and if you then iterate, you may really get this cooling down effect, right? So the probability or the value you have there, it starts with 0.9 and then it slows down to 0.5 and levels out. It's a kind of not vanishing gradient, but vanishing probability value, or I don't know what you want to call it. So these are big challenges, but we have to, because come on, I don't want to have to learn everything in AI from scratch again. I want to make use of the scientific knowledge that is around. I want to make use of simulators. I want to put them together. And for that, we need abstraction. I can't imagine that we would like to program everything in propositional logic. This must be hell on earth.
Yeah, so actually the question that Anna posed and you answer is similar to the question by Jefferson Fialho, how best to combine symbolic knowledge with data. Let me use that to ask one question myself. Mm-hmm. So it seems like you're saying we use tractable models, should use tractable models. But when you do logic, when you do Problog, a language that you'll be involved in, when you do things with relations, when you work in a certain level of abstraction, tractability goes out of the window. So, yeah, right. So how do you see the tractable models interacting with untractable stuff?
Yeah, so there are two interesting directions in that. So first of all, I agree with you, but I was not saying let's forget about intractability, or let's forget about NP hard problems or whatever. I think this is, my AI teacher was Bernhard Nebel, and he was always telling us, look, if it's NP hard, the fun starts. Okay, I agree. That's where science starts. It's okay. But to see how far you can get with tractable models is interesting. And I'm not sure that we need all the time the full NP hard approach. And let me illustrate that. So in mathematics, if you want to have a multivariate Poisson distribution, it's tough because the link function, the normalization may not converge, or no one knows really how to do it, right? And then you find in the literature all these approximations. Now, if you take a probabilistic circuit here, it's very simple because you approximate this more complex, whatever it should actually look like, by a deep mixture of univariate models. And univariate, we know. So now seeing how far we can get is amazing. There are cases, of course, where you would like to have the proof that it always works. And this is where we need this more complex stuff. But for me, AI as research is not always about being always correct. That's maybe then the wow if we manage. But I like to say that if I can match the average human, that's already tough enough. And definitely, They are not solving all the time every NP problem I'm giving them. So I'm with you, Fabio. As said, I like to work on problems that are NP hard. But I don't think that this implies we should not try to understand how far we can get with tractability. And maybe it's a bit like what Kahneman was saying and what also Gigerenzer is promoting, that in standard situations, we should use the tractable stuff. So it's a bit like a system one, so the bit more like reactive, we know the answer and we only have to compute it. And then we have in parallel running somewhere the more complex thinking machine. And the question is how to get these two machines in a concurrent way together.
All right, yeah, it's tough to see the path forward. But so we have a number of questions still. I'll try to condense a few of them so that we don't take too long. But there's a few questions, like, for example, by Gianea, Thiago, Edson, that touch about biases and values, ethical behavior. Maybe you can say a few words about how do you see ethics and AI interacting and worries that AI brings to this matter.
Yeah. So first of all, as said, I don't want to pretend that I'm really a person that is a hardcore AI ethics researcher, right? I think there are people really working on it, and maybe you should trust them even more than me. But what we wanted to contribute is this understanding that it's not only about bad stereotypes. Don't forget the good stereotypes that we are all working with. So that was my main claim. By now, people call it, like Orientazioni, they try to call it machine ethics. So it's not the AI ethics in a sense of we as a community should understand how to set up AI systems in an ethical way, but it's also how machines can maybe develop or have an ethical compass or whatever. So, and I think that is interesting. Now, if you really think about the implication, as a society, we decided that if a system is conscious, that we take care of the system, right? It's not that it's a machine anymore. And I think acting in a moral, valid way is getting close to conscience. And I don't know whether I want to care about all my algorithms, whether they are really my babies. So we can definitely think about it. But I also always like to think about the dual way of it. So actually, sometimes maybe I'm less interested in the machine. What is very interesting, in one follow-up work, we were using these moral compass idea to see how moral norms were changing over time. And so it's so much more fun to also learn about us. And I think that is also interesting. Or as I illustrated, then actually we wanted to build a very practical tool that tells us in your image data set, maybe you don't want to use this image, or at least you should be aware that you use images of Hitler. It's very practical. So what I also want to always say, let's have always both views in there, but there will be the point where you need a regulation, where you say, okay, maybe we don't want to go further. But that's, for me, also very natural. I mean, come on, from medicine, we know that you don't want to clone humans. We decided that, and it's fine. And I think it applies here at some point as well. And we don't want to maybe clone a complete, to get an AI system that can have the all same capabilities as a human. No, but understanding so that we improve. So, for example, working with cognitive scientists, is it really a flaw if we do something wrong? So in pandemic, we were also asking that again. I think also in Brazil, people are very fast in always saying, you did the wrong decisions 5 days ago. To be honest, maybe 5 days ago, it was an optimal decision. Maybe not a good decision if you have more knowledge, but back in these days, maybe it was optimal. And so with our tools, with our algorithms, we can provide an argument to that and put it on a scientific basis. And I think this is a very strong argument that we learn so much about us. So this is also, in my opinion, what Josh Tenenbaum is a bit arguing for, although he's also playing, of course, the card of saying, what can AI learn from the humans? And so, but also let's have the dual view on it. And as said, I'm a friend of no, only because it's possible, we may not have to do it. It's very clear for me. I'm not I don't want to clone Fabio. I'm sorry. It's enough that we have one Fabio in a positive way.
All right. Yeah, well, I wouldn't do that too. But, well, let me take a final question. So it's by Caio de Beraldini. It's an interesting question. So I think it touches on things you mentioned in your talk. So maybe it's a chance for you to reinforce a few ideas. So he says, well, could there be a jack of all trades learner, an algorithm that learns everything with enough data? I think your point is like we have to be more flexible, right? So maybe you can say a few words.
Well, okay, I think that's also a longer debate. You may argue there cannot be this one learner because there is no free lunch theorem. We can now debate and discuss a bit what are the assumptions on the no free lunch theorem, but assuming that it holds, you may argue, no, it cannot be. Now, I said, I don't care about the optimal learner and finding the optimal model. I cared about getting a model that is working well enough. So that is not what the free lunch theorem is talking about, right? If you're always a bit below, for me, that is fine if I'm epsilon away. So maybe there is a chance to get something like that. And in a sense that the existence of humans indicate that there's something that seems to work pretty well on average in a very robust way, right? So I think it's possible, yeah. And why shouldn't we find it at some point? But maybe this takes many, many ages, and I don't think I will see it happening. But who knows? I guess it is doable. But is that really the only goal of AI? I think what we see is we want to help other disciplines. We want to help in making in earning money and running business. We want to make scientific discoveries, and that is an engineering question as well. And if I just have to engineer, let me give you the example that Ad Artsen, he's a neuroscientist, he was giving to me when I was a PhD student. He said, Christian, I'm a neuroscientist, so I unfortunately have to stick to what the brain is giving to me. But now imagine that you want to understand how to navigate at night and there's no light. You as an engineer, you can use infrared. Be happy, go ahead. Me as a neuroscientist, I can't because I want to understand the human brain, so infrared is no option. And I think that makes the point clear. From an engineering perspective, I think we just want to combine the best systems that we need to solve our task, and that in a safe way. And that seems to be systems AI. It's very interesting. So again, like what we know from AI classes, if you want to understand the human, that's maybe a slightly different game. If you just want to build rational systems, I think it's very valid to ask it from an engineering perspective. And it's anyhow fun to work with software engineers, programming language people. You know, you get this new view on computer science. They don't like it sometimes, but they have to smile when I run around and say, look, this is all AI. We can just call computer science AI and get a new perspective on computer science. I don't mean it completely serious, but it's really fun. All of a sudden, you get always new ideas about how to improve databases, how to improve programming, how to improve chip design. It's fun. It's a lot of fun.
All right, Christian. So I think we have to close. I mean, there would be many questions. So I think you even touched on causality, which is in itself as an endless debate. I would have questions, but well, let's close, and let me thank you very much. It was great. Thanks a lot. Thank you for the audience, and we'll see in person at some point. We'll see each other when we can. Okay.
So you're invited to Germany. I'm happy to come to Brazil, or we meet at any of the conferences.
Oh, please come. Please come and then face some Brazilian summer, which we'll see. Yeah. Different one.
Awesome. I have been in Brazil. I enjoyed it, and in Brasilia in particular. So that was fun.
Okay, good. Well, thanks a lot. Bye-bye. Bye-bye, everyone.